So, how's everyone doing this week? Hanging in there?
We're
I'm,
getting ready for a blizzard tomorrow.
how are you? Okay.
They were talking 70-mile-an-hour winds with snow.
Oh, wow. Wow. Hmm.
We've also got very high winds and snow, but it's supposed to be in the 40s also, like mid to high 40s. So I'm not sure what this is actually going to look like. Be very interesting. It's going to be melting as it falls.
That's
I
great.
missed last week because I got this thing, one of the things at least that's going around. So
There's a lot going around. Hope you're feeling better.
here is, yes. I
No.
am, and go to the doctor when you get it, perhaps, because you may need an antibiotic because it's pretty nasty.
Yeah. Yeah, a lot of people are coming down with all the stuff right now. Well, let's see. Last week we were supposed to finish modules 1B and 1C. I totally forgot. So, like the week before, we started 1B and 1C, which is Radio Moon, Radio Jupiter. Got halfway through or most of the way through. Can't remember. I have to check. Um, and we were supposed to finish it up. Take our radio. Yeah. I remember now. We spent a lot of time learning how to put in a radio observation, how to process the data when it comes back, and we ended up with those radio images of the moon and Jupiter and calibration sources. And then we're going to do something with it. We're going to measure brightnesses, calibrate them into Janskys, convert them to temperatures, do a little bit of introductory radio science. But I forgot. So, because, I'm doing stuff with my students and I'm doing stuff with you all. And I guess I just got mixed up. I'd finished it with my students and I was on to star clusters. So I started that with you all. Anyway, we'll finish that next week. We'll come back and actually wrap that up. So, there's a punchline. I just kind of left the joke hanging there. Um, so last week instead, we started Star Clusters Module 2, and we made our preliminary images. So we learned how to take the individual images and clean them and align them and stack them and group them and color them and calibrate them and have some what I'm calling preliminary images because there's still one more thing we have to do to them that we haven't done yet, and that's correct for the dust along the line of sight. So we get the actual colors of the stars, but we don't have that number yet. Going to measure that today, along with some other things. Okay, so I think where we left off is we had made the preliminary images and we did batch photometry. The images we did red, green, blue, but also I-band. So we had four filters and we photometered every star in all four images. So typically 3 or 4,000 stars, something like that. Well, it depends on density of the field. And everyone picked a different. I gave you three. I gave you a young open cluster, an intermediate age open cluster, and an old globular cluster. And that's how the module's broken apart. It's into three age groups. And you each did one of them. And that kind of, it's similar to what happens within the student groups. They each do one and they do the photometry, but then they share the photometry files. We're going to take that photometry, turn it into HR diagrams, but it's important that you do all three. Doing just one is not going to teach you stellar evolution and achieve the goal of the lab. Kind of the goal of this module is at the end, that each team does their three images, young, intermediate, old. They do the HR diagrams, they measure ages, they correct for dust, they look at their HR diagrams, their images, they relate components. Oh, they're the main sequence stars, they're the red giants, there's the horizontal branch, and they really make that connection. And then what we do is we pair them up with a different group and they swap images, color corrected images. At that point, we've calibrated their intuition. And so it's really remarkable. I'm surprised how well this works. Um, they get these images from the other group. And so they have six, three that they know really well, and then three others. And they just they do two things. They put them in chronological order, just looking at them. So three new ones came in. They don't know their ages, but just looking at the pictures, they sort them. And then we ask them to guess their age in log time. And usually they get it right within a factor of two or three just by looking at the picture. And that's really impressive. It means they really understand what's going on with the stellar evolution and all that. Okay, so that's kind of where we're headed today. You need to get the photometry files. So in the email that I sent around, there are three CSV files. And as I just said, you're going to have to do all three. We're going to do them together. And so grab all three from that email. I'm already sharing. So while you're doing that, I'll just remind us of the three clusters that we did. So here's our young one. Some of you did this one. IC 2395. It's the first one we'll model the HR diagram. Prompt 6 had a pointing error when I collected this. These are the three I did this time. There are only 5 images, this year, this cycle. There are only 5 images deep in each filter. And anyway, the pointing error, the cluster is actually off on the side here. But we'll look at these carefully in a little bit, but you could tell this is a young cluster, some pretty bright blue, massive stars getting down. The fainter it gets, the redder it gets. That's main sequence. Then our intermediate age one was NGC 2818. Intermediate age cluster, it's looking a little red to me, so I bet there's some dust along this line of sight. And there's a little planetary nebula there just for fun, happens to be there. That's the intermediate age cluster, so not as many blue stars, certainly, because the massive blue stars, they burn out first. And then we did a globular cluster, NGC 4590. This is really crappy data. This is kind of an ugly picture. I think 2 or 3 of the images were taken in Chile, and the other 2 or 3 were taken Meckering, Australia, which was kind of out of focus, as I think Clues pointed out last time. Anyway, it's all combined here. And so we have this glob, and we all know that as stars evolve off the main sequence, the stellar distributions get redder. So this one's a bit of enigma, enigma. There we go. It wouldn't come out. See all these blue stars in here. What the hell? What are all these blue stars doing in a glob? And so we'll try to wrap our mind around that as well. Okay. Do you have the files ready to go? Okay. You want to go to Clustermancer. Well, Astromancer is a suite of tools. Let me go to the main page. On the main page, we just have the Opus tools. We've been adding some MWU ones, and we want cluster, and I'll put the link in the chat here. Cluster Astromancer. This tool is awesome, though sometimes when loading the data in, it's a little glitchy. And I'm hoping Reed will work on that, because other than that, this is the most gorgeous tool we've built. I love this thing. Okay, so let's start with the young cluster, which was IC 2395. So I'm going to add that one in. IC 2395. You got to type the name in. Be sure you get it right. Hit next. And so that one worked real fast for me. It'll spin a little bit, and then it kind of stops, and then it's a solid progression, and then this box pops up. If you're still spinning, then you may have to, cancel. Sometimes it helps to refresh the browser. Usually takes me 2 attempts to get stuff in here. Anyway, did everyone get to this page? Okay. Next, I forgot to describe what was on the box, but basically it said you had this many stars, and I forgot to describe what was going on. So it took your photometry and it was cross matching it with the Gaia catalog. So it's finding your stars based on the RA deck, finding the stars in Gaia, because Gaia has obviously distances. Gaia is the mission that we launched to measure parallaxes to like half the galaxy. And it has proper motions because it's been doing it so long. It's watched these stars move across the sky. So parallax is the distance, and proper motion is the tangential motion. And it's real subtle. It's milli-arc seconds per year, but this thing's precise enough. So we've cross-matched, and for most of your stars, it found a match. And then it takes us to this page. Okay. And I know some of you've seen this before, but some of you probably haven't. So I'll just describe what we have here. We have the proper motions here. This is a 2D plot. This is not the distribution of the cluster stars on the sky. Actually, I can't even call them cluster stars. These are the stars in your image. With open clusters, most of the stars in the image are unrelated. They're foreground stars, background stars, and anyway, this is not a plot of their position on the sky. This is proper motion space. This is the motion in RA versus the motion in DEC. And the thing about a cluster is it formed out of a cloud of gas, and that cloud of gas had some motion, and when it collapsed, all the stars inherited that motion. So there should be a clump in here. And this is actually probably a good one to start with because it's a little challenging. Sometimes it's real easy, like in the next one would be real easy. In the globs, almost everything in the glob is part of in the image is part of the glob. But the open cluster here is actually a very minor constituent of this field. So we got to find it. And you can kind of see a hint of it. This is the right ascension histogram, the declination histogram, and usually the brightest spike is cluster. Now, this lets you zoom in. The top one lets you zoom in. And so I'm going to kind of zoom in closer to that spike. The bottom will let us crop it around that. Already I can see it. There it is. And I'm going to zoom in the deck axis as well. If it's obvious, I normally start with the lower sliders, which is shrinking this circle. A lasso. We're going to lasso the cluster. But this one, it's really subtle. It's this concentration right here. So you have to go looking for it sometimes. Now we're going to lasso it. So I've kind of constrained it there in RA. Going to lasso it in DEC. Zoom in a little bit more. And I should say there's this thing that if you zoom in beyond the edge there, it's like crap, I just cut it out. And you have to go here and recover it. So if you push this too far, it actually pushes the lower one. Zoom in a little bit more, kind of frame it up. Oops, I did it. Did just what I said.
Dan, can you say a few more words about like what you're looking at? Are you just trying to find the peak of the histogram or
Yeah,
you're focusing
well,
more on the
I'm focusing
proper
more on
motion?
the plot here in the middle. Once I zoomed in, I saw the clusters, this overdensity. I'll zoom out a little bit so you can see it compared to the field stars. Zoomed in a little bit, and you can see there's the concentration right there.
Right.
And so then I zoomed in more. At this point, I'm really trying to lasso it in this plot. I'm kind of framing the histogram, but really, as I'm doing this, I'm looking at the middle plot.
Dan, do you usually have some kind of rule of thumb as to how big that lasso should be? Should it really be tight around it? Should there be a little bit of kind of like space around it? What insight do you have?
It's a great question, and it's not addressed well at all in the module. Um, I guess kind of like what I just did. So I try to get it kind of close to where I see the overdensity, but not cutting into it. Now I could tighten it even more if I wanted to, but that's pretty good.
Yeah, and which one are you looking at?
IC, whatever the IC one was.
395. Okay.
Yeah. IC is usually the younger clusters get that IC designation
Right.
instead and
Okay.
NGC. Okay, so I framed in proper motion space. We can slide down. We probably should have looked at this beforehand. This was a color magnitude diagram, but I've already cut out 93% of the stars. This color magnitude diagram was a mess, and now it's starting to look very much like a main sequence. But that was just proper motion. We can also frame it, crop it in distance. Now, with the open clusters, they're all very close to us, and the globs are very far away. So I'm going to start by zooming in a lot. If you have to do more than you can with the little cursor there, you can actually, oops, I went too far, which means I have to push this back out too. You can change the numbers here as well. Okay, that's pretty clean. That all looks like main sequence. There's some scatter at the bottom, but there will always be some scatter at the bottom because those are your low signal to noise stars. So those two stars, even though they don't look to be on the main sequence, they have the right proper motion, they have the right distance. They probably just have a large error bar in color. Anyway, I've now cropped out 94.3%. So this is a pretty extreme example where most of the stars in the field are field stars. Everyone pretty much here?
Dan, so just real quick,
Yeah.
kind of going more about the selection process that you were doing. So are you kind of just looking at all the different plots at the same time? So for example, when you were adjusting the proper motion for RA and DEC, you were looking at the peak, but you were also kind of looking at that scatter plot in the
Yep.
middle top to see if that corresponds to like a over density. And
Yep.
then you're also looking at the HR diagram to see if you see some sort of main sequence. So you're kind of looking at all parameters at the same time,
Yeah,
right?
in theory, you're looking at all of them. In practice, I was just looking at these three initially, and mostly the middle one.
Okay.
As I was lassoing this over density, I was looking at the middle plot as I was moving these sliders. And then I came down here to clean it up. And actually, it's good to do a little test. If you come here and put your cursor on the word field stars, those dots in the lasso, they have the right proper motion, but not the right distance. And they look to be the same density as the rest of the field stars. If there's an overdensity there, I cut into the cluster when I was doing my distance cropping.
Okay.
And you can know to back it out a little bit then. Anyway, that's a good one here. There aren't going to be too many stars in this one. And then we go to fetch archive. Now, we can add, we're not going to do this. I'm showing you the Skynet instructions. There's a whole nother set of instructions that Daryl Jansen came up with. But we can add catalog stars from Gaia, from 2MASS, from APAS, and from WEISS. And so when we build HR diagrams, we can build them with Skynet data and all these other missions. In fact, on the front page, we didn't need to load a Skynet file. We could have just started with archival data. So this tool can be used in any classroom, whether they have access to Skynet or not, which makes it really powerful. I wrote my module around the Skynet data, naturally. And in my instructions, I say, okay, we do it with Skynet first, and then we go back and we add in the archival data to improve it. But although the archival data often goes deeper, Gaia goes deeper, 2MASS goes farther red, there are some calibration uncertainties from filter set to filter set, and I don't think they really add too much in terms of improving the accuracy. And so this year I'm experimenting with my students, not even doing the archival data, just purely off the Skynet data. So that's what I'll show you today. I'm not going to add any catalog stars, but if you want to, you could play with that there. So let's proceed right to isochrone matching.
Dan,
Yeah.
before you jump over there, just real quick for clarification, when you're saying that you are using your students doing their Skynet photometry files, that does that mean that you are very carefully curating the clusters that you have your students view to make sure that they have like really good photometry and they are not in a weird part of the sky with too many I don't know, sort of like field stars?
Right. Um, they're picking them from a provided list that Daryl put together. So it's curated the targets have been curated. As they're starting to model them, particularly that first run through the proper motion and distance cuts, they can have a hard time. Sometimes it's not obvious where the cluster is, like the case we just did. We had to work a little bit to find it. So I have my TAs all throughout the room kind of looking over their shoulders, and I showed them some examples. And this takes multiple days to do this. So each day I show them a relevant example. And the first pass, I think, is a little bit rough, but I'm fortunate that I have enough eyes throughout the classroom that they get good at it pretty soon after they do the second or third. But no, I'm not like checking each one very carefully, or personally anyway. All right. Okay, isochrone matching. Let's build two HR diagrams. So strange no distance here. I'll put that in 0.71. So normally it fills in a distance. Basically, on the field star removal page, the median value here, 0.7, it normally starts with something like that. And it tells you here what the field star removal value is if you want it. And I'll show you how to do that. I was just kind of surprised. I think since I hopped back and forth so much, it lost the value that was in there. Anyway, to build the HR diagrams, on the x-axis, you have color, and on the y-axis, you have some measure brightness, luminosity. Okay, so let's do the x-axis. So here, I'll just create one first, and then I'll explain. So I'll do B minus R versus V for one of them. I'll add it there. So, you all know this, right? The brightness in one filter is not its color. Just because it's a blue band doesn't tell you anything about the color. It's the difference of the magnitude in two filters. So you take a bluer filter and a redder filter and subtract their magnitudes, and that's the color. That's what we have on the x-axis. And on the y-axis, we take, I often just pick one in the middle. So if it's B and R, V's in the middle. And this, that's a measure of brightness, but here we convert it to an absolute magnitude. And so that's a measure of luminosity. And you have your choice. You can do a color magnitude diagram, which is apparent color versus apparent magnitude. The lab's written in terms of HR diagrams, where this is intrinsic color, so dust corrected color, and this is absolute magnitude. So that's analogous to luminosity instead of brightness. Okay. Let me put the other HR diagram in here. It's often good to have two covering slightly different wavelength regimes. So we did B minus R versus V. So let's do V minus I versus R. V minus I versus R. And that will fill up the screen real estate. Now keep it in standard view just for the time being. Standard view, it's kind of fixed. And so I can, move the isochrone around without the data moving around. And then frame on data is also an option. And we'll use that particularly with the older clusters. Anyway, we have, this is the isochrone. That's the curve of constant age, isochrone, same time. So all these stars form together, but they have different masses. The high mass ones live up here and the low mass ones here. And I do spend some time explaining stellar evolution and walking them through what's going on in the cores of the stars as I evolve this. And there's a video about that. Yeah, I won't bore you with all that, but if you want to see how that would be explained to a student using this tool, there's a video on that in the website. Oh, Varsha, your hand's up.
Yes, then I'm trying to do this, but my diagrams are not showing up. So I do believe uh, I got to the fetch archive point and I had loaded the uh, CSV file so I could see the previous set of figures, but now nothing is appearing anymore.
On
What
your,
could I be doing wrong?
did your field star removal page look kind of like this when you were done with it?
Let me see. Not quite like that, but yeah.
So you have some stars left over and it looks kind of like you have a color magnitude diagram looks something like this.
Yes, yes. I do. I haven't really removed it, anything, but
Okay. Um,
yeah. I mean, I did narrow down the range of proper motion array and proper motion deck, and
okay.
so yeah, I do have my color magnitude diagram does look like that.
Okay, good.
But
And
then I
then-
did fetch archive
Okay. And then proceed to isochrone
and
matching.
proceed to isochrone matching, and then nothing appears.
Okay, you have to pick B minus, you have to design your HR diagram for it to appear. So,
Oh, I see. Sorry, I thought the blue and red meant it actually shows B and R, but okay.
no, you pick your filter. So the
Okay.
first one here I did was B minus R versus V. And then once you
Okay.
fill those in, there's an add button.
Right. Okay. So
Okay. And
thank
then
you.
sure. And the second one I did was V minus I versus R, just to give one a little bit redder.
Okay. Thank you.
Sure. Okay, so let's see what happens here. Distance, fortunately, that's kind of provided by Gaia. With the open clusters, it's pretty accurate. With the glob, the globs are farther away. Gaia is not as accurate, and you'll have to play with the distance for that one, but not really for the opens. You have age. And so as I increase the age, you see the hot massive blue stars, they become red giants. Moved over here, became red giants on the red side. And as we get older still, we get a horizontal branch. And older still, that horizontal branch grows as the low mass stars populate the blue side of it. Again, I spent a lot of time explaining what's going on in all the steps. Metallicity is also important. It changes the opacity. So the globs, they're really old. So it's primordial gas for the most part. And it's very low metallicity. So it's like 1/100th solar. Here's 1/10th solar right there. Solar is 0. It's a log scale, and 1.0 would be 10 times solar. And so open clusters, they're newer, formed in the plane of the galaxy. The gas has been enriched. So the open clusters tend to be over here, and the globs tend to be down here. Set that in a second. And then EB minus V, this is the intervening dust. And this is the intrinsic diagram. It's the HR diagram. So it's been corrected for distance. So if I correct for dust, if I say there's some dust there, it corrects the data point. It makes the stars brighter, moving them up, and bluer because dust reddens. So if I take the dust out, correct for the dust, the intrinsic values become bluer. Okay. So now we're going to model this. Again, for the open clusters, we don't have to worry about the distance. It's mostly 3 parameters. Now, I should say sometimes you may have a stray. Well, in standard view, it doesn't matter. But okay, so here we go. I normally start with the age. I'm going to up it until I come to the turnoff point right there. Metallicity, this is an open cluster, so I want to be kind of over here somewhere. And I'm trying to match the curvature. Somewhat. We'll see how it goes. And a little bit of extinction. Now let's see. This is a young cluster. Oh, there we go. If I keep it pretty young, I get that little shelf. See that shelf there? There we go. Need a little bit of dust, not much. Push it up and touch there. See how it's going through there? lift it a little bit. Anyway, you can spend a lot of time fiddling with this. Oh, yeah, that's getting nice right there. The farther down you go, there's more uncertainty. So the point should kind of straddle the line near the bottom. But for the rest of it, the point should mostly be above the line because of binaries. Half those stars are actually doubles, and so they're brighter than you would expect. The single ones should touch the line, and the binaries should ride above. And this one's pretty good, but it's never going to be quite perfect. You can have photometric calibration problems and all sorts of things. But I'll let you all get to your own solution. Don't just mimic mine. And of course, I could sit here for 10 minutes and really get it in there perfectly. But just get best you can and give me a thumbs up when you feel pretty happy with it.
And if I can sort of back up to remind myself like how we got here. So last week we had these pictures that you started off by showing, and we went through and we removed like bad pixels and we stacked and stuff. And then at some point in there we did like a plate solve, I guess, to like identify
Yeah,
these stars. Is that right?
the images already had a WCS on them. So the last thing we did was batch photometry.
Okay. Which identified like specifically what stars they were in the sky.
Yeah, we
Because like
extracted every star in the red image and then photometered all of them in all four of the images.
and so then the CSV files that we uploaded were the ones that we finished last time
Yep.
by creating. And those CSV files have the Gaia data in them.
No, they don't. They have
Okay.
just the Skynet positions and photometry, calibrated photometry. And then when we stick it in this tool, that's when the cross match with Gaia takes place.
Okay. Okay. Thank you.
Well, how's everyone doing with their isochrone matching? I'm not going to give you too much more time, but tell you what, let's see, well, we'll see if we need more than a dozen. If you're doing it, stick your value in here. Claim one of the teammates. The first thing is the young open cluster. So go ahead and erase one of the teammates and stick your name in if you're doing it. If you're just, observing, that's fine. But otherwise, if you're actually doing it, get your distance, age, metallicity, and reddening in there for your match. I'll put mine there too. I'll do the first one. What'd I get?
Is this view only for everybody else?
Oh, here, let me check. Okay, there we go. And don't just try to match what I got, just do it yourself. And now we have the students in groups of four, and they're all doing this, and it takes time the first time, and they get faster each time, right? If this is your first time doing it, then it's you'll get real good at this real quick. You saw how quickly I did it, and you'll get there. Um, and they all do it, and then they kind of compare the results. They put their numbers in here. If anyone's wildly discrepant, they look at it and they discuss and decide whether they want to keep it, reject it, or if the student needs to go back and refine it. Um, let's see, why is this not working? Circular dependence detected. Okay. And so, we could see, we had a little bit of disagreement about metallicity, but it's not huge. We all kind of have it. Yeah, there's a little bit of variation with metallicity, but age, we're pretty consistent. I mean, we all got the age within a factor of whatever that is, 0.164, 10 to the, no, a factor of 1.5. That's pretty cool. The distance, of course, we're close because of Gaia, and we're also in really good agreement on the amount of dust. Okay, let's
Um,
do,
that
yeah, go
that's a
ahead.
good question. When you do this in a large class and teams are submitting things, how much of kind of like do you ever see kind of like cases where you get kind of like degenerate solutions that are just kind of like equally valid? Of course, we're not doing any chi-square or anything like that,
Yeah.
but I mean, how big of an issue is degeneracy of models to the data?
Okay, so you're not asking like monkey see, monkey do degeneracy, where they're just copying off the person next. But since the distance is well defined by Gaia, the degeneracy there's not much degeneracy. Once you get to the glob and you have to reintroduce distance as a parameter, you can get more degeneracies. But all these motions are different. Like the EB minus V moves you along the diagonal. The age whips the top over. The metallicity changes the shape, but it's not in one of those two directions. So I don't think the degeneracies are very strong. And I'm not trying to go for um, publication quality results. This is more the pedagogy of do they understand the stellar evolution? Okay, let's do another one. So I'm going to go back to the main page. Proceed. Let's open up the intermediate one. And we'll do this a little quicker. Maybe, we'll see. Intermediate, that's the NGC 2818. Okay, that one took as well. 1,000 stars, almost all of them matched. So this one's easier. You can really see the spike here. So once you get it in there, given that you started on a tough one, this is an easy one. You won't see it in the scatter plot until you start zooming in, but you certainly see it in the 1D histograms. See that really tight concentration? So we're going to have many more stars in this one than we had before. At this point, I'm watching the lasso in the middle plot, the scatter plot, more than I'm actually watching the 1D distributions. Once you've lassoed it, go down and check the distance. I'm good with mine. Did the final check by hovering over the word field stars and seeing which ones my distance cut took out. It looks to be the same density as the rest of the field stars, so I didn't cut too much in distance. Overall, I took out about 80% of the stars. The HR diagram, the color magnitude diagram is pretty good. I can see the turnoff point, and we have some red giants now. This is an older cluster. And whenever you're ready, just proceed to isochrone matching. Set that distance to the field star removal value, 3.27. Yep, that's about right. So 3.27, and create your HR diagrams. B minus R versus V, B minus I versus R. And I'll pause and wait till you get here. When you do get here, give me a thumbs up or something. Okay. Got 3 thumbs. 4.
I'm not sure if anyone else is having this issue, but like when I'm in the field start removal page, sometimes when I adjust the proper motion RA plots, the bottom sliders also adjust. So
Yeah,
you lose the peak.
right. So if you push it too far, I'll do it. It actually then starts pushing the lower slider. When you back out, in this case, they've been merged. And if there's no, you have to kind of slide it back out. So if you go too far with the zoom in, it actually pushes the cropping slider.
Okay.
And if you get totally lost, there's a reset button.
Okay.
It's the one drawback of this design that I don't really like, but we couldn't figure out another way to do it. Maybe we'll revisit it. Okay, so a lot of you are on this page, and I'll just say a few things and I'll let you all keep working then. So I got the B minus R versus V, the V minus I versus R. Now that they're getting older and more squished, you may want to switch to frame on data. Give you a little bit more room to work. If you do have some crazy outliers, you can cut down the max error bar, and that will get rid of the ones with the largest error bars, usually from the bottom first. So you start cropping away at it. Well, I took them all out. This one doesn't appear that bad, so I'll just leave it as is. And then, play with the sliders. Date this thing. This one has some dust in it. This is also a nice one in that you can't really get a solution that works perfectly in both plots. Here at the top, the stars are on one side for one of them, the other side for the other. You kind of have to split the difference.
Dan, can you show your filters again at the bottom? And then
Yeah.
how to get the second frame up?
B minus R versus V, and V minus I versus R.
Max. Let's see.
Yeah, this one's a little frustrating because it just doesn't fit at the top. It could be that our isochrone models are a little out of date, but probably it's a photometric calibration issue between these filter systems. And I like the V minus I minus R. That one fits pretty nicely. And when you get it, go ahead and insert your numbers.
Sorry, where are we supposed to enter the numbers?
I stuck it in the chat. This would be the intermediate one.
Dan, what does frame on data mean?
Yes, so standard view has a fixed range. And this is great when you're trying to explain stellar evolution because you can move the isochrone around without anything else moving. But sometimes, particularly with these older ones where all the high mass stars are gone, frame on data instead picks the range based upon the points in the plot.
Oh, I see. Okay. I thought this was a astronomy term I didn't know. It's just
No,
about
it
plotting the
is
data.
literally framing on the data. Okay, we're getting there. You're much faster this time. And let's look. We have even better agreement on the metallicity, a little bit more disagreement on the age, but still pretty tight. You know, more than a factor of 3 or less than a factor of 3 variation in the age. You have some differences in the distance, but okay. And then when you're done with that, on to the glob. Oops, let's see. And let's see, the glob was NGC 45. No, oops, that I loaded a PNG. That's not what I want. NGC 4590. Now, usually things work well when you practice and not when you do the live demo, but this Gaia lookup, it's like the opposite. Whenever I have a bunch of people doing it, it always works. Whenever I'm just doing it by myself, I always have to like 2 or 3 times to get in. Now, this is the glob. So almost everything in the field is part of the globular cluster. So I'm not going to be too careful with my lasso. And the thing about, oh, go
Just
ahead.
a quick question then. Should our lasso be actually circular or can they be dramatically ellipsoidal?
They can be dramatically ellipsoidal based upon this kind of framing on how much you've zoomed in one axis or the other. I'm demoing it now.
Gotcha. Thanks.
Now, here with distance, Gaia is not great. And often, unless I see a peak, I just kind of leave it alone in distance. The color magnitude diagram here looks great. See the horizontal branch, but the distances, it's just going to be kind of random all over the place. These things are just a little bit too far away for them to get a good distance. So, I mean, you can zoom in a little bit if you want. but it doesn't really matter. In fact, here's an example. I hovered over field stars and you see there's a concentration. I cut too much in distance there. I'm going to back that back out. These distances are really just erroneous measurements. See, that looks a little bit better. Anyway, basically taking everything in distance, most things in proper motion space. And you can start with the field star removal recommended value, 7.67, but you're probably going to have to adjust it with the glob. So B minus R versus V minus I versus R. Here it's really flat because we've wiped out most of the stars. We're getting down to the detection limit. So I'm going straight to frame on data. And I like this. I like globs here this old. This is when they get really old, if you have particularly a low metallicity. So remember, globs have low metallicity. So you're going to want to put that slider back down on that side. And then as they get old, that horizontal branch just grows out towards the blue. A little bit dust, but to get the horizontal branch to match, I'm going to have to adjust the distance. So this is mostly a game between distance and reddening. Reddening moves it on the diagonal. See, I got a nice through here. We got the turnoff point right down here at the bottom detection limit of our data.
Dan, quick question. For globular clusters, your isochrone fits should go below the H&R diagram's main sequence, but here I'm having a hard time picking up the main sequence. So is there a rule of thumb? Should my isochrone kind of like go through right through the middle, a little bit more towards the left, towards the right? What should I do?
So there are very few main sequence stars on here. It's all red giant and horizontal branch. So I don't know if you can see what I'm doing with it. What I'm trying to do is, once I basically slam the age to the right and the metallicity to the left, getting the right shape. The curve has the right shape of the data. I'm just adjusting dust to move it on the diagonal. And then distance to get the horizontal branch and iterating between those two. But once you feel good about it, put that in the table.
Dan, where did you get the distance? I mean, that was from the previous
Yeah, for
histogram,
this,
right?
yeah, for this one with the globs, I
Yeah.
start with the recommended value from the field
Ah,
search
okay.
page, but you have to adjust it with the glob because Gaia can't measure good distances that far out.
Right.
But fortunately, the horizontal branch gives us a nice thing to latch onto to get
Yeah.
that distance.
Yeah.
Now, this is a really old low metallicity, so you have a long horizontal branch. Some of them, the horizontal branch is quite small, and so it's a little trickier. Like 47 tuck is another example I was just working. Basically, the whole HR diagram is a straight up and down line. It's all red giant branch. It has a tiny little horizontal branch, but it's just, trickier. Let's see, where is that? Sorry, Seth, I think I overwrote your age.
This was 4590, right?
4590, yeah. We'll get these in here and then I'll kind of show you the rest real quick and describe what the students do with this. But yeah, looking at those standard deviations, we have decent agreement. A little bit of disagreement on the distance, but it's harder. Some of us are measuring 10.2, which is technically older than the age of the universe, but that's a limitation of the models. Okay. Well, we got those. Oh, go ahead.
I have a question. Can you go
Yeah.
back to the isochrone meshing page? So it seems like there's some good teaching to be done by switching back to standard view,
Yeah.
right? Because you can like talk about like what the past of this cluster is. I'm curious if you can like talk about like what is up with how wide all these stars are like at the turnoff point.
Yes. So, yeah. Sorry, I wasn't clear about that. The farther down you go, you're looking at fainter and fainter stars. And so you have greater and greater uncertainties. And notice the scale on the y-axis. Each tick is 5. And on the x-axis here, each tick is 1. So we've really stretched here. So suppose your uncertainty is in your magnitudes is, let's say, 0.2. Then that's a very small amount on the y-axis, but that's a much larger amount on the x-axis. And with color, you're subtracting 2 of them. So it'd be like times root 2, like 0.3. So the uncertainty really shows on the x-axis at the bottom. That scatter at the bottom is just measurement error in the photometry.
That's great. Thank you.
Nothing physical. And you can kind of see it if you take this max error and decrease it, it will start getting rid of points that have error bars that are too big, and see it crops it from the bottom first. Okay, in the final few minutes, I want to tell you what we do with this. We have values. Let me write them down. The extinction values: 0.12, 0.21, 0.06. Okay. So if you have your image loaded up from last time, you can do this. Otherwise, just watch me. I might go a minute or two over, just so we can finish the topic. But for IC 2395, we're now going to correct for dust along the line of sight. We go back here. We've already linked pixel value, photometric calibration. This is where we calibrated last time. Here we can correct for dust. Actually, let me start with the intermediate age one, because it had the most dust, I think, 0.21. Yeah, here it is. I'm going to come here. And just for example, I'm going to take out a full magnitude of dust. Suppose there's a full magnitude of EB minus V. See how blue it got? So there wasn't that much dust, but if there was, the stars were really super reddened, and now we fixed it. And this is kind of cool because most astrophotography software packages don't do color correction this way. This is a physical way to do color correction. Now we measured 0.21. Let me put 0 in first. Now I'm going to put the 0.21 so you can see the size of the effect. It'd be a little bit subtle, but wait for it. There. I don't know if you noticed, the stars were all kind of brownish before, and now we have this nice collection of blue whites and reds. These are the red giants. These are the turn-off point stars. Let me correct all 3 real quick, and then I'll just kind of walk you through the rest of this exercise. Describe it anyway. This one was 0.12. Real subtle. Then with the glob, we didn't measure much extinction, so it won't change the colors that much, 0.06. But once you get up to like 0.2, it starts to make a noticeable difference in color. I don't know. Let me put it to you. Should I explain the rest of the exercise now, or do we just pick up with this next time? Do you have 5 minutes, or should we just resume next time? Go for it? Okay. Okay, so the students then, you tell them to pull up, each image and each HR diagram. I think I have the HR diagram for this one right here. And they have to identify components. Here's the upper main sequence. These should be very bright and very blue. Well, here, and then working our way down here, here, here. The image is off center. The cluster is over here. And so you can find it. And as you go fainter, we find redder stars. And the fainter you go, the redder you get. Very faint, very red. So this one, you can see the main sequence in it. I'd normally spend more time explaining, but I think you get the gist. This one we've now color corrected. Before we color corrected, everything was really kind of reddish. Let's bring up its HR diagram. So this one, it turns off, and we have some red giants, and we have turn-off point stars of the same brightness, but these are red, and these won't be as blue as what we just saw in the young cluster, but kind of blue-white, and that's exactly what we see here. You see the red giants, you see whitish stars of the same brightness, and then as you work your way fainter to fainter and fainter stars, you're picking up stuff that's redder and redder. Of course, again, with the opens, a lot of the stars, most of the stars in here are unrelated field stars, so that's a source of confusion. But you can see it there. And then with the glob, here's our ugly glob picture. Still have that one up here. So the brightest stars will be the red giants, and then fainter down, we should have a population of stars that go from red to blue, the horizontal branch, and then we continue down the red giant branch. And so the brightest stars are indeed the kind of the reddish ones. And then just a little bit fainter than that, you can see this kind of collection of all colors going all the way out to the blues there. That's the horizontal branch. Those blue stars in a glob, it's the low mass stars populating the left-hand side of the horizontal branch. Then as you get fainter, you're working your way down the red giant. This is a crap image, but the really faint stuff down here, that's the turn-off point of the main sequence. You might have like here's 47 Tuck. And so this is a great image. It doesn't have, its horizontal branch is really stubby. It's not quite as old. And so it hasn't populated the blue side of the horizontal branch. But you see the red giants, they're the brightest. And then just a little bit fainter, you have whiter stars, that's the horizontal branch. And then it gets fainter and fainter and redder. And then this kind of, it almost looks like noise around it. That is the top of the main sequence. Anyway, they spend time doing that comparison, matching up what they learned with the HR diagram and stellar evolution with what's actually in their image. And then, as I described at the beginning, they swap images with groups and just look at the picture, look at their three that they calibrated, put them in order. They normally get it right or mostly right, unless there are two that are very close in age. You can easily flip those. And so they order them, and they put ages on the ones that the other group did. And they can normally get it within a factor of 2 or 3. And then, the groups then meet up and they discuss and make their arguments as for the order and the age, and then they share each other's values. And I'm going to do this with my students tomorrow, and I'll bring the table next time and show you how close they got to each other's values just by looking. Go ahead, Kent.
Do you have the list of clusters?
It's in the module. There's a link to Daryl's module in my module.
Okay.
Yeah. And he has them, and they have all the recommended exposure times to make this very easy for them. All right. Thanks for staying the extra 4 minutes. It was nice to just complete the topic instead of let it hang till next week.
Thank you, Dan.
My pleasure.
Yeah, thanks, Dan.
Thank
Thanks,
you,
Dan.
Dan.
That was
It's
awesome.
fun.
Hey Dan, a random question while you have a minute.
Yeah. Here, I'll stop the recording.
Okay.
I'll try to stop the recording. Where is it?